Welcome to this second session on time and frequency domain analysis. I started off last Monday on convolution, and I can see that already things are very difficult for students to understand. So I would really appreciate if you ask more questions so that I would know what is troubling you and what's bothering you and how we could address those questions. As I said on my very first day, this is a remote lecturing thing and not at all very easy on the teacher, because teacher has no way of knowing what students uh, uh, you know how students receive this. So in the absence of that, in the absence of any kind of feedback, it makes my life extremely difficult. I have no way of knowing what is happening. Okay, so please help me. We'll take short breaks every 10-15 minutes, ask questions, we will go through a discussion, and hopefully with that things would be better. Okay, so let me stop and look at what I was doing in the last class, which was to describe the method or the technique of convolution. Okay, so we defined convolution of two functions or two signals x and h, as if the resulting function is y, then we said the symbol used is x and star h, just like you have multiplication and addition, and this star means an improper integral from minus to plus infinity x of tau h of t minus tau d tau. So here the running variable is tau. So I described this last time as by taking h of t and representing it as h of tau, simply rewriting t as tau and flipping it. So by flipping I get h of minus tau and moving it to any particular t I am interested in, right. So I move it to a particular t and find out the overlapping areas between x and h for that particular t. For the overlapping areas, find the product, area under the product or integration is the value of y at that particular point in time in t, right. So with this I try to show an animation of a convolution of two rectangular pulses. I have shared that material, that file with you, so please in your spare time go through that file. It's a nice animation. It explains it's available in the course material, so please download, ask your instructor, ask your local manager to get you that file called convolution of two functions.pdf and play it, right. And then we can discuss in case there's any questions on that, or today if you want to ask questions on that after the break, we can ask questions, right. And I also demonstrated convolving x of t equal to e raised to minus t ut and h of t equal to ut, right, and that we went over in the class, and we did it. So today I will continue the study of impulse response, that is h of t. So given that for an LTI or linear time invariant system, we have this impulse response which is the output of the LTI system for impulse input, what else can we infer if I know h of t? I mean, if I know h of t, one thing I infer is definitely it is LTI, because non-LTI systems don't have the same notion of impulse response. What else can I infer? That's the first topic today, and what we can infer from h of t is whether the given system is stable or not. Right. The slide shows the mathematical development of that. I'll go over it shortly. All I'm saying is, given h of t, you can quickly infer, right, whether it is stable or not, right. So let me recall what is stability. Stability means if the input is bounded between a certain maximum and a minimum, that is input is not arbitrary value, arbitrarily large value, if it is going to be between minus and plus b, b is some value, output should also be bounded, may not be to the same value b but some value. So the maximum absolute value of the output should not explode. That is the idea of stability. This is also what is called bounded input, bounded output stability. Okay. So let me go over that. So I assume that the x of t max absolute value of x of t for all times t is less than b. Right? B is some limit. Okay, B is some limit. I'm not interested in that. It could be 10,000. It could be 0.1. Its actual value is immaterial as long as it is a finite value. Okay, so I find the absolute value. X can be positive or negative, and so that its absolute value is always positive for all times. I look at the maximum of that signal for all times. That maximum should be less than some value b, right? So given an LTI system, given that convolution holds good, what is the condition, right? What is the condition on h of t? Given h of t, I can say it is stable or not, right? So I know that convolution operation, I told you last time, is commutative, meaning x and h can be interchanged. So this can as well be written as h of tau, x of t minus tau, and integration is with respect to tau, right? This and this are equal, completely equal, right, for all times t. So I want to find out what is the absolute value of this. So absolute value of this on the left hand side equal to absolute value on the right hand side. That part is simple, right? If y is equal to this, absolute value should also be equal. So y is equal to this, so you take absolute value. Right? Now we start using our idea of logic, our idea of understanding of mathematics, of integration and summation and so on. Right? So what I say is, suppose I have a sequence 1 minus half plus 1/3 minus 1/5 and so on, right? So if there is a sequence where the alternate terms are plus and minus, okay, that will be smaller than the same sum where every term has positive numbers, meaning 1 minus half plus 1/3 minus 1/4 plus 1/5 and so on. This will definitely be less than 1 plus half plus 1/3 plus 1/4 plus 1/5 and so on, right? Because here I am subtracting out, here I am adding. So this has to be less than this, because here every term is positive, here some terms are positive, some terms are negative. Because some are positive, some are negative, that will be less than an equivalent, another place where everything is positive. So I make use of this idea and say that this absolute value of the integral is less or equal to integral of absolute values. I am saying this is less than this for the same reason this is less than this, because integration is like summation. In the first integration, some terms can be positive, some terms can be negative, and I am taking absolute outside, right? And that absolute is less than individual absolute, sum of individual absolutes, because when I take sum of individual absolutes, I am adding up only positive numbers. Otherwise, some can be positive, some can be negative. So I use the same idea here, and I know that integration is isomorphic with summation. Integration and summation, we know from our ideas of calculus, are similar operations. Okay, so absolute value of the integration is less than equal to integration of absolute values. Okay, if there are questions, I'll take it up after the break. So this is now equal to absolute value of h tau and absolute value of x of t minus tau. but I have assumed that the maximum possible value of absolute value of x is less than b. So I can replace every value of absolute by b, right. So this will be less or equal to where I have b replacing x, because by assumption x is less than b, so this will be less than this, b comes out. So this is equal to b absolute value of the integral of h of d tau, right. So I have assumed that my input is bounded. For my output to be bounded, this integral should be bounded, b is bounded, so this will be bounded only if this will be bounded, meaning so the condition is h of tau d tau absolute value, this integral between minus to plus infinity should be less than some m, it should be less than infinity, that's all. This is the condition for stability. This is a condition for stability. So what it says is, given an impulse response, if the impulse response is absolutely integrable, this is in mathematics called absolutely integrable, meaning I can take its absolute values and integrate, and if that integration is finite, right? If the integration is finite, then that is a condition for stability. Okay, so given an impulse response, check if it is absolutely integrable. If it is, then the system is finite. Okay, so I'll take okay, maybe this is a good point to break, right. We'll take a short 2-3 minutes break, look for questions, and then come back and look at given impulse response, how do I say it is causal or not. Okay, so now I've said given impulse response, I know whether it is stable or not, okay, whether the system is stable or not. Okay, so I will pause for a couple of minutes for questions. Okay, some questions are coming, very good. So this is from PSG college. It says, does it mean systems are stable if h of t is decaying function like h of t exp? Correct. Well, I don't quite agree a of t ut, because a of t ut will make it complicated. So the question is, if I'll write here, if h of t is of the form a of t ut, right, where presumably a is positive. If a is positive, this is a decaying function. This is a decaying function, and if you find its integration, meaning if you do e raised to minus at 0 to infinity because of u dt, right, this value I think is 1 by a. This value is 1 by a, and a is some finite value, so it will be stable. So this integral is less than infinity. So an impulse response which is decaying exponentially, right, and defined for positive values of time is a stable system. Yes, the answer is yes, right, but that is not only that's not necessary. I mean, it's an overkill. If it is, it's okay. This is a sufficient condition, right? It's not a necessary condition, but nevertheless, it's a good thing to ask. So again from PSG Tech, e raised to minus at ut where a is greater than 0. Okay, so I already answered that. Then from PCP, PECPY, right? If h of t is ut, is it stable or not? Okay, killer question. Okay, this is a complete killer question. I won't answer the question. I want you to tell me if h of t is ut, is it absolutely integrable or not? Okay, just based on that, you tell me whether it's a stable system or not. Okay, so I will not answer it straight away. I leave it to you to figure out and then come back and argue with me one way or the other. Okay, so first find out if h of t ut is absolutely integrable, right? I will when you are trying to do that, right, I'll also ask you to show that 1 plus 1 plus 1 plus 1 sequence, so on, right, that infinite summation of 1 1 1 1, whether that sequence converges or not. Please find out how to show that. I want each one of you, right, in this course to at least mathematically prove and convince yourself that 1 plus 1 plus 1 up to infinity does not converge, right. It's an exploding, exploding sequence, right. So I wanted to show that. So please, and for the same reason, integration of u of t also is not a converging series. Okay. Then the question is critically stable. The question from PSG Tech, which is a comment on the previous question whether u of t is absolutely stable. It says critically stable. At least it is not bounded input, bounded output stability, right. I don't know. There could be different forms of stability. Mechanical engineers talk about saddle form stability, saddle point stability, and so on. So, uh, you know, for us, I have defined stability as bounded input, bounded output stability. So h of t is u of t. It is not. Okay, that part is clear. So I don't know whether it's critically stable or not. Then, so let me then continue with my impulse response study, right. So I will now look at um, given h of t, right, what can you say about causality? Can you determine just by looking at h of t whether the system is causal or not, right. We define causality to mean a system where the output depends on outputs at a given point in time, depends on the present input and the past input, right, not on the future inputs, not on the future inputs. So any system where the output depends only on the present and the past inputs, right, is a causal system, right. I mean, it's like many physical systems. I mean, my favorite example is a banking system or a financial system where because you are putting the money, you earn interest, right. Just because you have intentions of putting the money next month, bank doesn't give you interest today, right. So putting the money is the input, earning interest is the output. So first input is there, only then is the output, right. It's not other way around, but in causal systems this part is violated. Okay. So the question is, given impulse response, what can you infer? Can you just by looking at impulse response say this system is causal or not, right? And the answer is, it is possible given the nature of convolution integration. Let me consider this integral and let me draw x of tau. So this is my x of tau defined for all tau, right, and let's take h of t and find out h of t minus tau. Okay. So this is the time t, this is the input, what is shown here shaded, this is the input up to time tau equal to t, right, and at this time I want my output to depend only on this, not on the future inputs. That is the requirement of causality. Okay, at a particular point in t, my output should be based on the present and all the past inputs, not on the future inputs. Okay, so let's see now how does that relate to the convolution relationship with the output. So I've defined output as input convolved with the impulse response. So I've shown here h of t minus tau, right. So if I want my output to depend only on up to time t, then you see that my h of t minus tau, right, should be 0 here. If it is non-zero here, then this and this will overlap. Even for time t, it will give you output, right. So one requirement is at time t, h of t minus tau should be 0 for tau greater than t. For tau greater than t, it should be 0. Right? Otherwise, they will have overlapping areas where you can find the product and find the area under the product for y at time t equal to t. Okay, in which case causality will be violated. So for the system to be causal, the impulse response, in this case the flipped version and the delayed version to t, this part should be 0, right. So I'm saying h of t minus tau should be 0 for tau greater than t, right. So by simply this means this is the same as saying h of t should be 0 for t less than 0. This condition will ensure that. If the impulse response is defined only for non-negative time, okay, that's a causal system. Because if you make sure of that, if this part is 0, okay, then in this case, because tau greater than t is 0, so I will get minus infinity to t x tau h of t minus tau d tau, because beyond that it is equal to 0 by the requirement, right. So this means, okay, this means h is 0 for non-negative values of t, for non-positive values of t. So on this side, so h of t is defined only for 0 and beyond, and on the left side it is equal to 0. This will ensure this property, and so the upper limit of integration can only be t, and it will not be it will not violate the requirements of causality. So one more result, and then we are ready to take another break. So it's now possible that we interconnect many systems, right, one after the other. Any practical system is not just one system. There will be many filters one after the other. So my X goes into one system, right, let me call it as hash 1, that's my system 1. Its output, let's say, is x1 of t, goes to another system, let me call as hash 2, and so on, and hash n, then the output is y of t. Any practical system is complex. The input goes through the first system, the output of that goes to the second system, and so on. Finally, I'll get one output. So this is what is called the tandem connection, one after the other, right. So the question is, can I represent this entire thing by one system, so that when the input is x of t, I get the same output y of t. Can I represent this entire tandem of n systems where the output of one goes to the input of the other, and so on? Can I represent this entire thing as one system? The reason this is important is all practical systems, right, are not just one system, but consist of multiple systems where the output of the one processor is given as input to the second processor, and so on. So that's the interconnection of systems. So in this case, a second interconnection also is possible. Second interconnection is what is called the parallel connection. Same input goes to two systems. Two systems or more than two systems, and the output is added up. Output is added up, right? So is it possible to represent this entire thing by one system? What will be the nature of that? So the answer is, if both are LTI system, if this is LTI, right, then I can write out the convolution integral, that is x of, let's call this as y1 and this as y2, and impulse response of this as H1, impulse response of this as H2, then Y1 is X convolved with H1, Y2 is X convolved with H2, Y1 plus Y2 equal to Y. So you can write out all this and show that this is equivalent to a combined system whose impulse response is a combination of the two impulse responses H1 plus H2. Then if the input is Xt, I will get the same output Y of t here. So this is a parallel connection. When the input goes through two systems and their outputs are added up to give me the final output, it's as if the proof is extremely simple. Straight follows from our idea of convolution, our idea that integration is a linear operation. So in this case, the two add up to give me a combined impulse response. Okay, so this is parallel connection of systems. Next, I talk about the tandem connection of systems, one after the other, and multiple things are possible, right? One is if you connect systems one after the other. Let me for example just take two systems rather than n systems for the purpose of illustration. And if they are LTI systems, suppose the constituent systems are LTI, impulse response is H1, H2, then the combined system will have a new impulse response H of t, which you can show is convolution of H1 and H2. Individual impulse responses can be convolved. That gives me the combined impulse response, for this tandem connected system. This and this are joined together and give me a joint system H of t, right? And because convolution is commutative operation, right? For LTI systems, this means an interesting result. If I first send it through a system impulse response H1 and the output of that goes through H2, this is identical to first sending it through H2 and then sending it to H1. The order can be interchanged. The order can be interchanged. Right? So for LTI systems, when you have a tandem connection, right, the nice thing is it doesn't matter whether you perform this operation first and the second LTI operation next, right? The order doesn't matter, you get the same output. You can interchange the order, right? So all these results will make sense when we're actually designing systems, right? A bigger system could be more complex to design or more complex to implement. It can be broken up into smaller parts, then maybe the computation is easy and so on. So sometimes a tandem connection is preferred to a more complicated system like this, right? Sometimes reversing the order makes it extremely simple to analyze rather than a system where it goes through a more complicated impulse response first and maybe a less complicated impulse response next. That would be a complex system, whereas if you reverse the order, so LTI system gives you immense flexibility, right, in analyzing, in building, in designing, in testing and so on, right. So I think this is a good time to take another short 2 minutes break. We'll wait for questions. Okay, so please ask questions before we move on to another topic. Okay, so let's see some questions. This is from PECTN. The question is, if h of t is a complex exponential, what about stability of the system? Okay, so this is very similar to the previous question, which was if h of t is u of t, right? I didn't answer. I didn't say whether u of t is absolutely integrable or not. If x of t is e to the power of j omega t, you take its absolute value and see if it is absolutely integrable, right? So convince yourself whether if h of t is a complex exponential, whether it is absolutely integrable or not, right? You can perform this simple operation and then get back to me, right, in case you have any doubt. Check out whether if h of t is a complex exponential, whether it is absolutely integrable. If it is, then the system is stable. If it is not, system is not stable. Question from MCKV, it says h of t is u minus t. Is it causal or anti-causal, right? So I did not define what is anti-causal, so let me not bring in new word. I'll just say causal or non-causal. Okay, but anyway, it's a good question. It says given h of t in the form h of t equal to u of minus t, meaning this is u of minus t, is defined for t 0 and all values of t less than 0, negative values of t it is defined. Again, I will not answer this question. You first tell me whether h of t equal to ut, whether that system is stable or not, whether that system is absolutely integrable, right? Same result holds good for this also. If you can answer that question, you should be able to answer this question. Same arguments, right? So there is no difference between u of t and u of minus t. In one case, it goes in the positive direction of time. In the other case, it goes in the negative direction of the time. So if you can argue for one, the same arguments hold good for this. Just the time is flipped. Okay. So please answer that question. This question is from GIT JPR. I presume it is a GIT in Jaipur. So I'm very happy to see people from Jaipur here. The question is, sir, what would happen when ramp signal will convolve with itself? We're getting into interesting questions here, because some textbooks tell you that if x is u, that is unit step, if you convolve x with itself, right, if you convolve u of t with itself, unit step with itself, this result will be a ramp function. This will be a ramp function. Okay. Now let's call this as some y of t. If you now continue this operation, right, if you convolve y of t with x of t, y of t I obtained by convolving x with x, meaning unit step with unit step. The answer is t into ut, which is ramp. Oh, I erased that, huh? So it's still here. Okay. So ramp is this function. So y of t is this is a ramp, right? It's a sloping function, right? 45 degrees line, sloping function, and the equation is t, y equal to t. That's the answer for the first part, convolving u with itself. Then if you carry out the operation sequentially, right, once again, right, if you do it once again, y of t with x, right, what will happen, right? I think it becomes t square. It becomes paraboloid function. This probably becomes t square u of t. The question that is asked here is, what happens if y of t convolve with another y of t? So remember, x of t are defined as unit step. I convolve x of t with itself, you get a ramp. You convolve the output, that is ramp, with unit step, you get t square. That is a paraboloid function, right? So if you convolve a ramp with another ramp, what happens? Okay, I don't know the answer, but let me try to find out, right? So at a particular point in time, it will be something like this. So this is the product, this function is t, right? Well, it's tau here, somewhere here is t, and this value is 45 degrees. So it is tau minus t, tau minus t, yes, no, minus tau into t, yeah, minus tau plus t. That's the equation of this line. This is tau, this is this. So you are convolving, so tau minus tau plus t d tau, so that's equal to integration of minus tau square between 0 to t and plus t and tau dt. 0 to t. So you get um, what do you get? Tau cube by 3 0 to t, right? Um, why did the things change there? Why did the things change there? Okay, I'll have to come back to see that. Plus t into tau square by 2 0 to t, right? So you get t cube by 2 minus t cube by 3, that is t cube by 6. Okay, so good. So when you convolve a ramp with a ramp, you probably get t cube by u of t, a rapidly increasing function in the positive direction of time, exponentially increasing t cube. We can go on doing this. It's not a it's a nice for those people who are interested in maths. But remember, we are talking about physical systems here, right? And please remember that impulse and u of t and complex exponential and all, these are the signals we have defined to make our life easier, right? So remember, we use them to represent some physical fact, right? We're not mathematicians trying to work with u of t or delta of t and so on, right? So to that extent, I'll urge you to don't speculate too much about all these things. I mean, it's okay. I mean, it's good to know that, right? It's good to know that we have defined them to make our life easier, right? But please don't make your life more complex by getting caught up with these ideas. Okay. Another question from PhD Tech. It says if H of t is a low pass filter and H2 is a high pass filter, they are in tandem connection. Can their connection be interchanged? I mean, why not? If it's LTI system, why not? Right? Um, you know, as long as both are LTI systems, doesn't matter, right? Doesn't matter at all. We could do one first and the other next. So a tandem connection didn't put any condition. It says, as long as you have two LTI systems, you can perform the operation, right? Without worrying too much about the order, because convolution operation is commutative. That's all, right? I mean, it could be high pass, could be low pass, or whatever. I mean, its actual shape is immaterial. Question from SITH: give some practical examples where the convolution is used. Mobile phone. The fact that you are using mobile phone to make calls, there's lots of signal processing happening there. There are lots of filtering operation taking place there. There are lots of convolution taking place there. Okay, inside the mobile phone. Right. Today, you cannot talk about any audio visual system without convolution. Right. All filters are implementations of convolution. All radar systems implementation of convolutions. All automotive systems are implementation of convolution. So life is convolution. I can't, I mean, I might be exaggerating this point a little bit, but wherever any electronic processing of signals is taking place in your life, that is convolution. If you take ECG, that's convolution, right? So you're asking for an example. I'm saying your whole life today revolves, every technology uses convolution. So in that sense, you just have to get into it, and deep inside there is convolution. A similar question there, ramp convolved with ramp, right? There is a Laplace inverse relationship. I mean, I didn't talk about Laplace transform here. Like I said in the beginning, don't get too much into the mathematical properties of impulse response and unit step and everlasting complex exponential and ramp, and then more processing of ramps. I mean, it's okay. All I can say is, the entire mathematics is consistent, right? Otherwise it won't survive. This entire mathematics is consistent, right? There are no inconsistencies. What is true in Laplace transform is true in time domain. I mean, Laplace transform, I'm thinking in the frequency domain. So they're all consistent results. Okay. If something doesn't work out, it probably means that we have not applied that result well, okay, but the result by itself has survived for 300 years. It's very consistent. Okay, so in that sense, you can try to do ramp convolved with ramp in Laplace domain, and that's okay. No surprises there. Hand raise. Okay, very good. Okay, so MCKV, please ask the question. Yes, I can hear you, MCKV. Please ask.
So when two constant functions convolve with each other, what is the result?
A constant functions. You mean of the type of u of t, something like that. If x is u of t, that's a constant function. Okay, okay. I see. I understood. So let me draw that on the board. I don't know if you can see the board here. So the question is, if x of t is constant for all times, let's say some value 1, take it as 1,
Sure.
right? Take it as 1. If I convolve this with itself, right, what happens?
Yes, sir.
Okay, is that the correct way of putting the question, right? X of t is constant, right? So like I said, the entire study of systems is from practical system point of view, right? And from practical system we abstract out some principles and study them. So in that sense, u of t is not a very practical signal. If u of t is not a practical signal, this thing which is constant for all times is not even a practical signal, right? Um, and so by itself, this cannot be convolved by straight away, right? I mean, if t goes from minus to plus infinity, when you shift it, when you flip it and shift it, that still goes from minus to plus infinity. So to me, it appears that the integral is improper, doesn't converge. So convolution is not defined. Okay, but nevertheless, it should be possible for doing convolution in small parts by breaking up the problem into smaller domains, right? Uh, uh, Please ask. Yes,
If one function is constant function and another is step function, then what?
one
Any
is a
possibility
constant
is there?
function.
And
One is a
another is
constant
step
function.
function, unit step function.
A
Another
function,
is unit step function, and
yeah.
another first one is constant function, unit constant
Hmm,
function. Then
hmm.
any possibilities of convolution is there?
No, right? For example, I can tell you, if you take u of t as one function, u of minus t as other function, these two functions cannot be convolved, right?
Constant
Uh,
function is not convolved with, cannot convolve with step function.
Forget about that. Even simpler, even a question that is broken up into smaller parts, like if u of t does not convolve with u of minus t, because you get an inconsistent result, right? The integration doesn't exist, and what you are saying is seems to be something like that. A constant with a step function is like a constant with a step function convolved with u of minus t, right, which doesn't exist. So my answer is no, right? And I'll also ask you, why do you want to do that, right? Where do you see that kind of a problem appear? And if you must convolve, all I'm saying is this entire time and frequency domain theory is consistent, right? Some problems can be solved in frequency domain. I don't even know whether this one can be solved in the frequency domain, right? So my hunch is, I've not tried this, but my hunch is this cannot be done. Okay, meaning the integration does not converge. Okay, good. So let's continue um, the next part, which is the motivational part for what I'm going to do next, which is the frequency domain, right? So what I'm saying here is, you take an LTI system, an arbitrary LTI system with impulse response h of t, okay, and you give a specific input. If you give a specific input such as e to the power of st, where e to the power of st is an everlasting exponential, right. I think in the example I have given e to the power of minus st, so it's okay, e to the power of minus st. E to the power of minus st is an everlasting exponential. Something is wrong there. Yeah, I think the e to the power of minus st, should I want to say e to the power of st, t minus tau, yeah, well, I think it should have been e to the power of st. So the explanation given on the slide is wrong. I have to go and change it. So if the input is e to the power of st or e to the power of minus st, doesn't matter, right? What will be the output? Where s is the complex frequency which I talked about last time, and this is everlasting, meaning it has no beginning, no end, right? Everlasting. So what happens? What will be the output? What will be the output? Because it is LTI, convolution holds good. So let's let me try convolution. So I say, okay, y of t is x of t convolved with h of t, or it's commutative, so h of t convolved with x of t, so it is h of tau x of t minus tau d tau, and limits is minus to plus infinity, but x of t takes a particular value e to the power of minus st. So let me substitute for that. So that's equal to h of tau e to the power of minus s t minus tau d tau. Wherever there is t, I replace that with t minus tau. Okay, I think I should have been careful with e to the power of st, because now I'm seeing here that strange things are happening. Yeah, so I think I'll show e to the power of st as the input, e to the power of s t minus tau. I think I have to go and change my slide there. Okay, I was not very careful when I prepared that. So now you see this is e to the power of s into t into e to the power of minus s into tau. So e to the power of st can come out. So I have e to the power of st minus to plus infinity h of tau e to the power of minus s tau d tau. This is tau is a variable of integration, so it integrates out. Only s is the unknown. So this will be the result of function of s, right. So let me call this as capital H of s. So it's h of s e raised to minus st. So the output will be h of s into e raised to minus st. So very interesting result. So what it says here is, for an LTI system, if you apply an input e to the power of minus st, a complex everlasting exponential, s is the complex frequency, then the output also is e raised to minus st, no change in the output, right. You get the same everlasting complex exponential of same frequency s at the output. This is input, this is output, except there is a complex scaling factor hs. Because s is complex, this integral can become complex. So this is a complex scaling factor, which is a function of h of the impulse response, right. So when the input is e raised to minus st, output also is e raised to minus st, except it will be, it is scaled by a scaling factor h of s. You know, this is an idea that's of immense practical interest, right. What this says is, if the system is LTI and the input is of a certain frequency, output, you will see the same frequency, output frequency will not be different. So consequence of this idea is, LTI systems preserve the frequency, right. A big application of that is our entire electrical power grid, right. I can generate power today in Uttarakhand, I can bring the power, I can generate at 50 hertz, bring it to Tamil Nadu, nowhere will the frequency be different, it will be 50 hertz everywhere. Okay, so a big reason for that is the entire electrical grid is a linear time invariant system. Whatever be its impulse response is immaterial. But what is interesting here is because it's an LTI system, frequency is preserved. At the output, I get the same frequency. Maybe voltage is different, right? Maybe the phase is different. Voltage and phase are captured by this complex exponential, right? They undergo change, right? So this feature of linear systems, that linear time invariant systems preserve frequency, is very important. Okay, they do not change the frequency, they do not generate new frequencies. Okay, a corollary to this is if a system generates new frequencies which is not present in the input, then it cannot be a linear time invariant system. It has to be necessarily a linear time invariant, a linear time variant, or a non-linear system. Okay, so this very useful property of LTI systems, right, where I apply e raised to minus st at the input, I get the same output. So for this, e raised to minus st is called the eigen function of the LTI system. It's an eigen function of the LTI system. Similar to the eigenvalue, eigenvectors that you study in your linear algebra course, right? If there is a square matrix A, you multiply the square matrix with any arbitrary vector, the resulting vector will be rotated and scaled version of the original vector, except when it is an eigenvector. When you multiply a matrix A with its eigenvector, then the vector is simply scaled and the scaling factor is the eigenvalue. That is the interpretation of eigenvalues and eigenvectors of a matrix, right? The eigenvector after multiplying with A simply undergoes a scaling change, right? Direction does not change, it is in the same direction, it undergoes a change in its value. So e raised to minus st is an input, output also is e raised to minus st, except for a change in its value, right? Its amplitude might decrease or might increase, but the frequency does not change. So that is the interpretation. So we say e raised to minus st is an eigen function of LTI systems. Okay, and if the input is eigen function, output is the same frequency with some scaling factor h of s, which is given by this. So let me write that here. So h of s is defined as integral of h of t e raised to minus st dt, minus to plus infinity. This is the definition, and because it's transferring an input to the output, it is called a transfer function. H of s is called a transfer function. So this is the definition of H of s. So based on what it is doing to the input and output, H of s, let's call it as transfer function. Okay, we'll not discuss that here in this course, but it has a lot of applications in other areas like controls and circuits and so on. So what I do is I will take a short break now, or maybe I can introduce a new topic, right, and then take a break. Okay, so this is the foundation for going from time domain to frequency domain. So at this point I stop the time domain analysis, I go to the frequency domain, right, where the fundamental property I exploit is the idea of eigenfunction. An LTI system for input with e raised to minus st, output is the same frequency e raised to minus st with some scaling factor h of s called the transfer function defined by this integral. Right. So this idea that linear time invariant systems preserve the frequency, right, leads to the study of linear systems in frequency domain. That's what I'm going to do next. Okay, so that's the motivation. for switching to frequency domain. Okay. So I'll ask questions. So please ask me questions. Let's take up some questions here. PEC college. It is not e raised to minus st eigenfunction of the system. Is it not e raised to minus st? Yes. So I'm saying e raised to minus st is the eigenfunction of the system, right? But the idea of eigenfunction comes from eigenvalue and uh, uh, eigenvectors of linear of matrices. So in fact, there is a isomorphism between LTI systems and the linear algebra theory, right? Oh, you can represent one in terms of the other. Okay, so there is a connection between the two. So we use similar language. There we say eigenvalue and eigenvectors. Here we say eigenfunctions. So the idea is very similar. What is so okay, the question is from CIT Coimbatore. It says, what is the application of LTI system? What is the application of LTI system? Everything. If you ever have a CT scan, that's an LTI system. If you ever have an ECG done, that's an LTI system. If you ever turn on electric light in your room, that's an LTI system. So what is the application of LTI system? And LTI system is, we are surrounded today. All technology today, are built using LTI systems. Otherwise, the frequency frequency of generation at NOR power plant will be 48 hertz. At home, it will be 52 hertz. Right? That doesn't happen. Whatever the frequency here is the same frequency there. Right? So that is a property of LTI system. So if you ask the question, what is an LTI system? You are surrounded today by LTI systems. From PSG Tech, similar to H of S, can we define X of S to clarify? Well, you look at my definition of H of S here on the screen. Can you see this? Can you see this? Okay. So if you see here, I mean, H of t is some signal, right? I can replace H by any signal. I mean, as long as that improper integral is defined. Remember, the limits of integration are minus to plus infinity, and I said on the very first day, when the limits are from minus to plus infinity, please take a pause, take a step backwards and see if that integration is defined. If that integration is defined, you can put any function here for which that integration is defined. So I can have H of S, X of S, Y of S, Z of S, whatever, doesn't matter. PSG College has a long question. A JK flip-flop in its toggle mode acts as a frequency divider. As per your view, LTI system should preserve frequency. Does it mean JK flip-flop in its toggle mode is not an LTI system? Wonderful, right? The charger you use to charge your mobile is not an LTI system, because when you plug in, the frequency there is 50 hertz. At the output, it is DC, that is 0 hertz. So frequency is destroyed. Input frequency is 50 hertz, output frequency is 0 hertz. So that is not an LTI system. So when I said you are surrounded by LTI system, here is an example where, so wherever the frequencies change, right, they are not LTI systems. Okay. For example, in electronics, we have a thing called mixer, right? Mixers, I mix two frequencies and generate sum and difference frequencies. So because mixers change the frequency, they are not LTI systems. Yeah. So rule of thumb is extremely simple. If the input and output have the same frequency, then there's a big chance that they are LTI. Okay. If the frequencies are different, they're definitely not LTI. Right? Input frequency is 100 hertz, output frequency is 50 hertz, definitely not an LTI system. That you can be sure of, right? Other way around, you have to see what is happening, right? Meaning, if the frequencies are the same, is this LTI? You have to do more investigation, right? It may be that for that particular input, the frequency is preserved. For some of the input, the frequency is not preserved, right? But LTI system says, no matter what is the input frequency, at the output you get the same frequency with some arbitrary change in the amplitude. Okay, if this property is preserved, then it is an LTI system. Okay, let's continue. So we move on to what is called the frequency domain analysis of LTI systems, a new topic, right? So in this I will do two different subtopics, Fourier series and Fourier transform. This is my second class. So I have two more lectures on February 1st and February 8th. So altogether I have nearly 5 hours. So in 5 hours I'm going to do Fourier series and Fourier transform, right? So that's a pretty challenging idea. So hopefully I'll do a Fourier series in 2.5 hours and Fourier transform in 2.5 hours. So in 5 hours I will do the complete large chapters, right? And the motivation for that is this eigen function analysis, right? So the reason I want to go into frequency domain is I want to express my input signal in terms of the frequencies, because the moment I express my input signal in terms of its frequencies, I can take individual frequencies and give it to the input and see, I can predict the output will be same frequency with some different scaling factor. Okay, somebody is giving me a call. Okay, so let us start. Let us start with definition of a periodic signal. Right? So uh, a periodic signal, I say, is defined as if x of t is indistinguishable from its delayed version for a fixed value of delay such as capital T, then that function is periodic. If x of t is indistinguishable from its delayed version T naught, x of t and x of t plus T naught, I can't make out for some value of T naught, right? These are indistinguishable, they are identical, right? If this is true, if true, then periodic. Right? I can't make out x of t when I delay it. So take the example of a sinusoid. Let's say this sinusoid signal goes on forever. This is t equal to 0. Let's stand here. This is identical. Whatever I see here, whatever view I get at this point, I get the identical view on this side, right? So a thing is indistinguishable for some value of T naught, right? This is the fundamental property of periodic signals. Okay, it should be identical for some delay T naught, some advanced T naught. The smallest value of T naught where this thing holds good is called uh, so the smallest value of T naught is called the period. So the function is periodic and the smallest value of T naught is a period, okay, and 1 by T naught, well, T naught will be in terms of seconds, 1 by T naught is called F naught, the fundamental frequency in hertz, F naught hertz, this is called the fundamental frequency because T naught is smallest, right, smallest period. So F naught, is will be the fundamental frequency. We also say omega naught is defined as 2 pi f naught is the fundamental frequency in radians per second. So this is the radians frequency, this is the frequency in hertz or cycles per second. The two are interchangeable except for a change in the dimensions, except for a scaling factor. Omega naught is 2 pi f naught radians per second, f naught is cycles per second or 1 by T naught. So these are the fundamental definitions, and n times f naught or n times omega naught, they are called the nth harmonic, right? They are the nth harmonic. So I don't know if you know music, like in music you say sa re ga ma pa da ni sa. So the two sirs, right, are in music they are one octave apart. The second sir, the higher sir, is 2 times the frequency of the lower sir. Okay, so that is the octave or doubling of the frequency. So the first sir is the fundamental frequency, the second sir is the higher frequency or the octave or the it's the harmonic of the first frequency. So n f naught or n omega naught are called the nth harmonic. So f naught is called the first harmonic. Well, it's the fundamental frequency, or there is no first harmonic. Right? You have a second harmonic, you would have a third harmonic, and so on. So you got a fundamental frequency and you have the nth harmonic. Okay, this is the simple definitions. So omega naught is 2 pi into f naught. F naught is 1 by T naught, so it is 2 pi by T naught. So this means omega naught into T naught is 2 pi. This is another property that we make use of in several of our results. Okay. So these are all the basic ideas that I want you to be familiar with. So I have a periodicity, the smallest value is T naught. So that's called the fundamental period. Okay, and 1 by T naught is a fundamental frequency, it's called f naught. 2 pi f naught is the frequency, fundamental frequency in radians per second, and you have the nth harmonic, either n times f naught or n times omega naught, right? And so these are the basic definitions. With that, I'm going to now define some simple ideas, right, proposed first by Fourier. There are some interesting stories about Fourier. I'll talk about that. So Fourier said, if x of t satisfies this property, if x of t is periodic, right, then x of t can be written as a naught. Did I say a n here? Okay, a n cosine n omega naught t, n goes from 1 to infinity, plus bn sine n omega naught t, n goes from 1 to infinity. We said if x of t is periodic, then x of t can be written in terms of this trigonometric series. A naught is a constant. Somebody asked me a question before, a constant function. So a naught is a constant function here. Then if n is equal to 1, I have the fundamental frequency. N equal to 2, I have the second harmonic. N equal to 3, I have the third harmonic of both cosine and sine. And the amplitude associated with cosine is an, amplitude associated with sine is bn. So Fourier, this is something around 1830, so it's nearly 200 years ago. He suggested that any periodic signal could be written in this form. Okay, I will come back to this story little bit later. Let me first do a little bit of mathematics and then come back to the story of Fourier. Right? But my first question is, assuming T naught is a period, whether this represents a periodic signal, meaning the thing on the right hand side, does this satisfy the second property? Okay, so let me first write this as x of t plus t naught, substitute, replace t by t naught, replace t by t naught, and see what happens. Right. So you get a naught because that doesn't depend on time. I will not write the limits of summation all the time. It's very time consuming. Then n t plus t naught bn sine n omega naught t plus t naught. If you expand this, you get n omega naught t plus n omega naught t naught, but omega naught t naught we know is 2 pi, so it is n into 2 pi. So cosine theta plus 2 pi n is cosine. So that means this whole thing is cosine n omega naught. For the same reason, this will be sine n omega naught. So this is equal to x of t. So x of a delayed version by t naught is a period, I get back x of t. So the expression, this trigonometric expression that Fourier wrote, at least satisfies the basic requirement of a periodic signal. Then there are issues about how do you compute these coefficients, a_n's and b_n's, including a naught and so on. How do you calculate them? Okay. So for that, Fourier also gave simple relationships, based on the orthogonal functions, which is what I'm going to do next. So he says that cos n omega naught t, right? If you take a family of functions cosine n omega naught t, if you integrate this over the period t naught, meaning if you just take 0 to t naught or any t naught period, let me take it as 0 to t naught, if you take cosine n omega naught t dt, right? So what he says is, if n is 1, then I have one cycle like this, positive part is equal to the negative part. So this integrates to 0 for n equal to 1, this is n equal to 1, n equal to 2, 2 cycles. In one period t naught, n equal to 1 is 1 cycle, area under that is 0, n equal to 2 is 2 cycles, area under that is 0 because this is negative, this is positive, and positive will be equal to negative, area under the positive negative half. Similarly, you can go on looking at it for all values of n, 3, 4, 5, area under the curve will be equal to 0 as long as we integrate over one period. What is also interesting is you can start at any point, start at a and go to a plus t naught, a can be any value. In that, a running function, you can start anywhere, starting from there go up to t naught, you integrate, it integrates to 0, that is the property. Similarly, same thing holds good also for sine n omega naught t also integrates to 0. That is the first idea that Fourier said. Then the second idea is this set of functions, right? If you look at cosine set of functions, they are orthogonal, meaning if you integrate the product cosine n omega naught t into cosine m omega naught t over t, right, this will be 0 as long as n and m are different. So I have cosine n omega naught t here, I have cosine m omega naught t here, as long as n and m are different, distinct, then the product will integrate to 0, right, and that will be equal to t naught by 2, t naught by 2 if n is equal to m. If n is equal to m, then it becomes cos square omega naught t. You can write cos square omega naught t as 1 plus cosine 2n omega naught t by 2, n omega naught t integrates to 0 and you get half into t naught. So that is what it is, half into t naught. So this can also be shown quite easily. So he said the set of functions cosine n omega naught t are orthogonal. They are orthogonal because when n is and m are different, they integrate to 0. So whenever two signals integrate to 0, right, we say those two signals are orthogonal to each other. So cosine n omega naught t, cosine m omega naught t are orthogonal to each other. That is the second idea that he said. Sine n omega naught t is also an orthogonal set. What is true for cosine is true for sine. Then the another interesting property is the set of functions cosine and sine, they are mutually orthogonal, meaning if I take integrate cosine n omega naught t and let us say integrate with m omega naught t dt, this will be 0 for all n and m, even when n and m are identical. Here when I said if n and m are equal, then it is t by 2. When one function is cosine, other function is sine, m and n can take any value including identical values, right? They will integrate to 0, because if n and m take the same value, this will be, you know, a sine 2 times n omega naught t by 2. By the first property, sine integrates to 0, right? So this will always integrate to 0. So this collection of orthogonal properties, that is cosine function integrates to 0 over one period, sine function integrates to 0 over one period, the set of cosine functions are orthogonal, meaning n and m different, they integrate to 0, cos and sine are orthogonal, and sine forms an orthogonal set. So these, you know, 4 or 5 properties put together are enough to let us know how to compute the values of a naught, a n and b n. So only these properties are required to tell us how to compute uh, you know, to find the values of a's and b's, right? So I would like you to go home and show whatever I have shown here, that these properties hold good, just as homework exercise. So you can now show that if you integrate on both the sides, if you perform x of t dt over one period, I will show that as t naught, right? If you do the integration, then this will be a naught, right, into dt over t naught. This will integrate to 0, this will integrate to 0. So I will get summation of 0 plus summation of 0. I am integrating over a period, I am making use of the properties of cosine and sine functions. So from here you get a naught is 1 by t naught, because a naught into t naught, so into x of t dt over t naught. Given any x of t, if you want to find a naught of the Fourier series, then you carry out this integration. Okay, that's the first value, how you compute a naught. Right? Second value says, now you carry out x of t cosine n omega naught t dt. So you take x of t, multiply both the sides by some cosine n omega naught t and integrate over a period. This will be a naught into cosine n omega naught t. By the properties I described before, this will integrate to 0. Cosine and sine integrates to 0. In this summation, as long as m and n are different, they will integrate to 0. So only one property I am left with. So I get a n into t naught by 2. Right? So this is n, this is n. So this means a n is 2 by t naught into x of t cosine n omega naught t dt. That's how I can find out the values of a n. Right. Same logic applies in computing the value of b n. So you get, instead of x, you multiply with sine omega naught t dt, you get 0, you get 0, you get bn into t naught by 2. So you get bn is 2 by t x of t sine n omega naught t dt. So those properties are enough, those properties are enough to find the values of a naught, ANs and BNs is what Fourier said. Okay, and some more manipulations are possible. I will just describe two manipulations of the basic result that Fourier suggested. I don't know whether Fourier himself did this or not. So you can combine AN. This is a summation goes from 1 to infinity. This is a summation goes from 1 to infinity. So you can collect the terms of the same n and show that this is AN plus Cn cosine n omega naught t plus theta n, right. So slightly more compact expression where you can show that Cn is an square plus bn square and theta n is I think it's minus tan inverse of bn by Cn, something like this. Okay, let me just check. Yes. Oh, sorry, it's minus bn here, minus bn, and it can show this. I'm sure those of you who understand trigonometric identities, for them it is no sweat, can be done easily. So instead of having two infinite sums, I have only one infinite sum, so it's more compact, right. So this is one compact form of the same result. Okay, so the reason for going in for this compact expression is this says I have a cosine of n omega naught frequency of this amplitude and this phase value. So I can now talk about what is the contribution of each frequency for this signal x of t. So 1 omega naught contributes C1, second omega naught contributes C2, and so on. So I can find out the amplitude of each of those contributing frequencies. This is called the spectrum, right. This frequency contributes so much. You all have studied about white spectrum, in your optics class, different frequencies of light combined to give you the white color. So that's the notion of spectrum, right. How many frequencies are present and to what extent are they present, right. In this case, knowing the frequency, I can find its amplitude. And I can talk in terms of what is called the Fourier spectra. Okay. Another compact form is what is called the exponential Fourier series, where I don't know again whether Fourier himself did this. Instead of using sine and cosines and so on, I can write this as xn e to the power of j n omega naught t. Now n goes from minus to plus infinity. A different way of writing the same Fourier series. So basic form is this, but I can write it in this form, and by using the orthogonal properties of this, right. The nice thing is here xn is 1 by t naught x of t e raised to minus j n omega naught t dt. So remember, in the previous case, a naught, an and bn, we had different formulas. So in one case there was just 1 by t naught, in the other case it was 2 by t naught. So you would have to remember where to use 2 by t naught, where to use 1 by t naught. But in the exponential form, that asymmetry is not there. Everything is very nice. It's simply given by this. I will come back to why this form is important in a minute. And I'm talking about the proof of this. Again, I'm not proving this result, right. I come back to the motivation. Why is this not this form, but this form is useful to us for the study of LTI systems? Is any periodic signal is written as a linear combination of everlasting exponentials. Okay, and I can use the eigen function property. If this x of t, if this periodic x of t is given as an input to an LTI system of impulse response h of t, then I know that same thing will come out. So if I give input xn e raised to j n omega naught t output will be some xn with some function of h, I do not know what it is, and e to the power of j n omega naught t. Xn is a constant, it comes out, there is a frequency dependent scaling factor and the same frequency comes out. That is the beauty of eigenfunctions. So what this says is, the moment you tell me the system is LTI and the input is periodic, I can tell you what the output will be. This result follows from our idea of eigenfunctions, and that is the application of Fourier series that we are interested in. Okay. So before I take up some applications of this idea, let me now take a short break. I will tell you a story and then I will take a short break. Okay. So the story goes that Fourier proposed that any periodic signal could be written in this form, this complex exponential in this trigonometric form, and he, in his paper, he wrote how to compute a naught, an and bn, and made into a big paper and sent it to the French mathematical journal 1830. Okay, what do you think happened? Paper got accepted? So the story goes, paper was rejected and poor Fourier died without publishing his paper. Okay. Now if I tell you, if I ask you, why was the paper rejected, right? So it turns out that the editors of the French mathematical journal were all these people whose name you study in mathematics, Legendre of the Legendre polynomial, and several other top mathematical people were the editors of this journal, and they asked a very simple question, right? They said, Mr. Fourier, look at this, if x of t is a rectangular function and periodic, if x of t is a rectangular function and periodic, you are claiming that this function can be written in terms of a large number of cosine and sine frequencies. Yes, are you foolish? Are you out of your mind? This function x of t has discontinuities. So at these points I cannot differentiate them, right? Whereas on the right hand side I have sine and cos, I can differentiate them any number of times. They are extremely smooth functions. If you can differentiate a function, a number of times, that defines its smoothness. Sine and cosine are extremely smooth functions. You can go on differentiating them with respect to time any number of times. So Legendre asked him, how can the two be equal? On the left hand side I cannot differentiate this even once, on the right hand side I can differentiate this any number of times. So how can the two be equal? Paper rejected, thrown out, and Fourier died. Okay, so I think it's a good point to take a break. We'll ask questions and then see, we'll look at the applications of. Okay, so there's a question from PhD Tech. It says, what is the significance of orthogonal functions? I mean, that's one property. I mean, I don't know what is the significance. My weight is 65 kgs. What is the significance of that? I don't know. I mean, it's just one property, right? So, it's one property that we attribute to functions. If two functions are orthogonal, means their product integrates to 0, right? I mean, that's one property with which we just like we have a property called mass and so on. So that's one property of the functions, right? So orthogonal functions satisfy a certain relationship. That's all. The my motivation in going for frequency domain analysis is simply the fact that when input is e to the power of st to an LTI system, output is some scale version of e to the power of st, right? And so I'm trying to find out for various different ways of s, and in that the first thing was the periodic signal, where the frequency is well defined. It is either 1 by t naught or n times t naught, n times 1 by t naught, right? So that is my only limited motivation here. This is not a full course on Fourier series and Fourier transform. There is a question from GCEJG, right? It says, how can we relate coefficients in trigonometric and exponential Fourier series? If you have cosine, use Euler's relationship, express this as e to the power of j plus e to the power of minus j by 2, this as e to the power of plus j minus e to the power of minus j by 2j, and so then you can combine an and bn for n positive and negative, and which is what you can get the complex exponential Fourier series. So not difficult at all. So connecting up this with xn e to the power of j n omega naught t is not difficult, right? Use Euler's relationship. This is e to the power of j omega naught t plus e to the power of minus j omega naught t n, sorry, n omega naught t, right? N omega naught t n omega naught t by 2, and similarly here e to the power of j n omega naught t minus e to the power of minus j n omega naught t by 2j. So use this and collect terms for the same value of n, and you can connect up a's and b's with x's. Okay, I have that in my slide. I'll come back to it. So the other question is from PCPY, PECPY. Can any continuous bounded function have a Fourier series? I will modify the question to mean, can any continuous bounded periodic signal have a Fourier series? Answer is yes, because Fourier series is for periodic signals. I told you this is the basic property. Only when this property is satisfied, Fourier series makes sense. So the important adjective you missed out in your question is, it should be periodic, right? If it is periodic, the answer is yes. The question from CIT Coimbatore is, an LTI system can be an open loop or a closed loop control system. Yes, obviously. In fact, what I am doing is the preliminary requirement of a course in control system. So unless you do this course, you cannot do control systems, right? So this is a foundational course leading to a study of control systems, circuits, DSP, and which is what I said on the very first day. So a system can be open loop or closed loop, doesn't matter for us. The question from RITSDS: is there any condition of convergence of x of t as its expansion is an infinite trigonometric series? Good question, right? I've been emphasizing this point again and again. These are all infinite series, right? Infinite series, please take them with great amount of caution. Whenever there is an infinite series, you worry about convergence, you worry about the existence, and so on. Okay, so I have not talked about the existence of this. I have not talked about the convergence of this. I'll come back to do this. Today I just introduced and told you the story of life of Fourier, the mathematician Fourier himself, right? So the question is right. I mean, these are infinite series, right? And just like improper integrals, infinite series are very difficult to understand. Think of Srinivas Ramanujan. Right? I mean, Srinivas Ramanujan could just write out infinite series, right? And people asked him how. He was from a place called Namakkal, right? He was from this place called Namakkal. So there's a big temple in Namakkal. He said the Devi of Namakkal writes all those equations on my tongue. That's the explanation he gave. He said, how can you think of all this? How can you write this, as an infinite series? He says, Devi of Namakkal. Right? So that's the explanation you can think of. Infinite series are extremely complicated things, right? So whenever somebody gives infinite series, don't rush. Take a step backwards, think, and then answer. So RITSDS, another question: how can a non-LTI system be analyzed as an LTI system? We always analyze non-linear equations by linearizing them in the vicinity of certain values where they can be made linear, right? So non-linear systems can be thought of as linear in a smaller region, right? Like for example, any complicated line, you can say this is linear here, right? In this domain, it is linear. it is linear here. So you can always assume piecewise linearity and linearize them. Similarly, when the thing is not time invariant, you can look at smaller time scales where the values or the parameters of the system do not change. So you always, so you can have short term time invariance and linearity over a small region. So it's possible to make a nonlinear system into a short term linear and time invariant systems and apply this property. Okay, so yes, it's possible in many situations to use these results and apply them to nonlinear systems. Question from PECPY: what kind of function should be the scaling factor in exponential output? So I don't quite understand, this question relates to the scaling factor. I'll come back to that. I briefly talked about the transfer function and so on. That's an integration, right? So the question is what kind of function? I don't quite understand that, because the answer also is in the form of an improper integral, but nevertheless there is a relationship. I'll come back to it, right? I'll if not today it's already 3:52, so maybe next week I'll come back and we'll talk about it. Huh? Okay, so I have a little bit more time, so I'll briefly talk about one example. I think that's a good thing to leave you with. I'm interested in, given a periodic signal, I'm interested in computing values of xn, what's called the Fourier series coefficient, right? So in this slide that is displayed, I connect up the relationship between x and a's and b's, which was one of the questions. So the slide shown here mentions the relationship between x and a's. So but that's very easy, you can get it from the Euler's formulas, and anyway I would like you to go home and try this out, right? Please get this results. So what I want to do next is I want to define an x of t, right? In this case I've shown one period of x of t. X of t is an exponentially decaying signal e raised to minus t by 2, right, defined for time between 0 to pi. So at time t equal to 0 the value is 1, because e raised to minus 0 is 1, and at time t equal to pi it is e raised to minus pi by 2. Okay, so this basic function is repeated every t naught seconds. In this case t naught is pi, right? I've expressed t naught as pi. So you see that I sketch this function repeatedly, right? So by repeating this function I create a periodic signal, an arbitrary, a strange looking periodic signal, okay, where as I said t naught is pi seconds and f naught is 1 by t naught, so it is 1 by pi hertz, right, which is an irrational number, right? And pi is an ugly number, though we take it in high school as 22 by 7, it is not quite 22 by 7, it's some strange number, irrational number. So 1 by pi is also an irrational number, right? And omega naught, which is 2 pi f naught, right, turns out to be 2 radians per second here. So omega naught is quite nice, right? So for this periodic a signal where an exponentially decaying part is repeated every 5 seconds, I know the values of t naught, f naught and omega naught, right? I want to compute xn, the Fourier coefficient for this particular signal. I want to compute Fourier series. So I know that xn, xn is 1 by t naught integral over any one period t naught x of t e raised to minus j n omega naught t dt. This is the definition, right? So you take one period, substitute x of t for that and carry out the integration, which is what I'm going to do next, right? So definition, I've put out the definition of xn there, and then I substitute for x of t as e raised to minus t by 2 and carry out the I know that omega naught is 2 here, so it is e raised to minus j 2 n t, that is what appears in the integration, and carry out the integration, right. I leave that part to you. Please attempt and do the integration, and it turns out that after doing all that, xn for this particular problem, xn turns out to be 0.504 divided by 1 plus j 4n. That is the xn I get. So n takes values from minus to plus infinity. So just go on substituting value of n here, you get all values. So for n equal to 0, it is 0.504. N equal to 1, you get a certain value. N equal to minus 1, you get a certain value, and so on, right. So I now expand that. I compute xn. I expand this to show what is the dependency on each of those frequencies. So in this case, I have taken out 0.504 outside. So x of t is 0.504 plus 1, that is for n equal to 0, because if you make n equal to 0, then denominator is 1, numerator 0.504, which is what is taken out, and I have shown all those terms there for plus 1, plus 2, minus 1, minus 2, and so on, right. And so that's your x of t, and I would like you to see that your xn is complex, right. And if you do xn and x of minus n is plus 1 minus 1. In that case, it is 1 minus j 4n, right. N is negative, so one is plus, other is minus. This property is the complex conjugation property. So x of n and x of minus n, please notice they are complex conjugation of each other, right. This leads to what is called a conjugation symmetry property, right. Conjugation symmetry means their magnitudes are even symmetric and the phase is odd symmetric. So we'll come back to this later on. We still have another 2 days left, so we'll talk about this conjugate symmetry property, right. And I have now terms like plus 2t minus 2t. Does it mean the frequency for the given real signal plus and minus, are there negative frequencies? So with that question I stop today.